Okay, I think we're going to go ahead and start back up. Hopefully everybody can see my version of RStudio up on the screen. I zoomed in a little bit, so hopefully this is visible. If it's not, just send a chat message. Can you guys see in the room okay? Does it seem good size? Rebecca, is that visible to you?
Yeah. Hey, Brady, can you like move, the up and down divider? Can you move it to the right so we see more of the code and less of the list of
Yeah. Yeah.
packages, et cetera?
Yeah.
Yeah.
That seem okay?
Yeah.
Yep. Okay. Okay, so this is again getting into that first example. So again, we're going to walk through with this first example just to emphasize a lot of these key points, and then we'll build on this and go a little bit faster with the later examples for different estimators. But we really want to get some of the essential concepts down. All of these measures are going to rely on a pretty standard set of R packages. So in this first example, we're looking at tidyverse, knitr, and survey. So if you don't already have those installed and loaded, you can just run this first chunk in the example1.rmd file, and that will load these packages which we need for this particular example. So we want to make sure to not avoid this first step where we actually load the packages that are fundamental for this first example. I want to reiterate too that the video recording of the short course will be made available on ISR's YouTube page. So if you missed something from one of these examples or something wasn't clear and you want to go back and review it, eventually the video will be available on ISR's YouTube page. So don't forget about that. Okay, so again, we're looking at estimates of mean depression scores from the Census Household Pulse Survey. We're going to start in step one with estimates from the selected samples. So again, the typical approach people would use in practice. I would tend to doubt that people would just look at the unweighted estimate and take that for granted, but people do that. We've done studies of the analytic approaches that people take in practice, and even that simple step of using the weights and estimation is often ignored. So we're still going to include step one just to show what would happen in the simple unweighted case. So we have a CSV file that contains the data from the HPS that were used in this particular example that you can read in and look at. So that's what this next chunk is doing. We're reading in that x1 underscore HPS CSV file, and we're creating those binary indicators for all of these categorical predictors that we're going to be plugging into the SMUB functions. So this is the essential harmonization step. If we have binary predictors that are being used to fit our regression model to form the proxy, we need those same binary predictors and their means and variances and covariances from the population data source. So we're being very explicit here about forming those binary indicators, given that most of our Z variables were categorical in nature. All right. So that's essentially what this big chunk is doing. We're just using mutate to create all of these different binary indicators. And then we're going to look at what the first chunk of the resulting data set looks like, okay, before we go any further. Okay, so I'm reading in the data and then I'm piping it through this mutate function to create these different binary variables. And then we're taking a look at the resulting data set and the number of respondents. So I'm just going to submit this entire chunk all at once here. All right. So if we look at the, let's see, head of the data file here, bring this up. Okay. We see these different IDs of the different cases, the week of the survey, not essential to what we're doing. But then you see the weight, right? That's the weight that census computed. You see the values on all these covariates in their kind of raw form before we created these binary indicators. And then if you scroll farther to the right in this tibble here that we get from looking at just the head, you can see all these binary indicators that are being created here as true-false coding within R. So these are all these binary indicators that we'll use for the modeling and again to create those means, variances, and covariances for the overall population. All right. So I'm just scrolling through that particular table here. And then we can see that there are a total of 64,588 respondents in this data file for the selected sample. All right. So that's our first step, is just some data management as an effort to try to harmonize these variables before we get to subsequent steps.
Hey,
All right.
Brady,
So
before
yeah.
you go on, I just want to make a comment about this HPS data set.
Yeah.
So this HBS data set is the raw HBS data, but with a very subset set of covariates. So HPS is a lot of questions on this survey, lots of variables. So it's just the demographic variables that we're going to use. You saw the weighting variable and then the outcome variable. And the only data manipulation that was done before what we're doing here in the R code was to create the PHQ score. So the PHQ score here, you can see it's a sum of the 4 variables that precede it, but you have to subtract 1 from each of those first because that's the way the scoring goes for the PHQ. But I just want to make sure it's clear that not really much, the covariates were not manipulated before they got here. So if you went and downloaded the PHQ data set, you would see the same R Hispanic variable, the same E gender variable, et cetera. The PHQ4 score is the only like preemptive data management that was done to this CSV file.
Yep. I mean, just like any other application, you just want to be careful at this step to get all the variables you want. But really crucial for our approaches is this harmonization. Just making sure all those Z's are coded the same way in the data sources that you're working with. Okay, so this is just the selected sample for now. All right, so let's calculate the unweighted and weighted estimates. We're doing this using the survey package within R. And you can do a simple unweighted analysis within the survey package simply by not defining any design variables. So we're not declaring any clusters, any strata, any weights for estimation. We're just setting those all to kind of their defaults, which would result in a simple random sample design. So that's what we're using here with survey design. So we create that SRS design object with the data set that we just formed. And then we apply the survey mean function to that survey design object called hps1.srs. And we're looking at the mean for that computed PHQ4 variable. In addition to that estimate, we're then looking at a confidence interval for that estimate or for that mean, given the estimation from the survey mean function, given the standard errors. Okay, so I'll go ahead and run this chunk. Okay, so we see the unweighted mean is 2.76. Remember what the original range was between 0 and 16. We see a standard error assuming simple random sampling gave rise to the HPS. And then we see this 95% confidence interval. And again, big data paradox. You look at this confidence interval and you say, wow, we've got a really precise estimate of that mean for the population. Okay, there's not a whole lot of variability because we have such a huge sample size. We're good, right? Not the case, right? We're assuming that that unweighted point estimate is unbiased and that that interval is correctly centered on an unbiased estimate of the mean that we're looking for. Okay, and we're going to see here that's definitely not the case, despite the fact that we have 65,000 people. Okay, so we do this analysis, and a colleague comes back and says, "Hey, Bozo, you forgot the weights, right? Use the weights in estimation." You say, "Oh, my bad." Okay, so you go back to survey design, you specify that p weight variable, okay, which was designed by Census to compute unbiased estimates in theory, assuming ignorable selection. That's the only thing we change about the survey design statement here. Okay, then we run the analysis using that weighted design object with the weights formally specified. Okay, let's take a look at what this chunk produces. Okay, now incorporating those weights, our mean has jumped from 2.76 all the way up to 3.18. So clearly there was some bias based on the observables that the weights are accounting for. Again, assuming ignorable selection. So it seems like it was definitely a good idea to account for those weights. Those intervals come nowhere close to overlapping. So it clearly seems like our inference was shifting once we use those weights that were provided by Census. And now we say, oh, we're good. I made that mistake. I forgot the weights initially. Now I'm using the weights. Now I have an unbiased estimate. Again, this approach for non-probability samples assumes ignorable selection, 100%. Everything, all that bias we can adjust for is based on the observables, okay? That's the assumption that we're making here. And that's where our measures take this, again, one step further, allowing for the possibility of a non-ignorable selection mechanism, okay? So the weighting adjustments increase the estimated mean by about 15%. So clearly those weights are capturing some of the bias, okay? But the question we have to ask is, might there still be non-ignorable selection bias occurring, even after we adjust for demographics? Okay, and that kind of regression-based adjustment that we're looking at here. Okay, so the subsequent steps in the R markdown file are the steps that we need to follow to implement the SMUB methodology and the corresponding adjustments. I would say probably 95% of people analyzing HPS data stop right here. Okay, that's the whole point of this workshop, right? Is to say, let's go past the thinking that these weights fix everything based on observables. Okay, let's allow for this non-ignorable selection mechanism. So to do that, we need to first get those summary statistics for the Z's for all the cases that were not selected in our sample. And we're going to pretend that that's basically the rest of the US population outside of these 65,000 people. So we're going to get these aggregate estimates from that 2019 ACS data. All right, so to reiterate, we use the data from the 2019 ACS in a separate program to calculate the means and the covariance matrix for the covariate Z using the ACS weights. We then save, just for the purpose of saving time, that mean and variance covariance matrix as a separate CSV file. Okay, so that step of calculating those aggregates using the ACS weights was already performed outside of this RStudio file. We're just saving those results here for the sake of time. I just want to emphasize that that step is necessary to calculate the weighted point estimates of these different aggregates, right? So this chunk is just reading in that corresponding or those corresponding population level summaries, okay? So I'm going to go ahead and run this chunk, and then you can look at what that looks like here, okay? So the first row here contains the means of all these variables, and the key thing to note here, these are means of the binary recodes of those categorical variables. They have to match exactly with the means and the variable names of those binary variables in our non-probability sample. And if you have just a regular continuous Z variable, that name has to match exactly. Okay? So you see all these variable names are directly aligned and harmonized with that data management that we did for the non-probability sample. Okay? So you see all the weighted estimates of the population means, about 48.7% male, about 30.4% with some college education, et cetera, et cetera. That first row contains those means, and the subsequent rows contain the weighted variance covariance estimates for each of those covariate Z. For the standard maximum likelihood application of the SMUBs, all we need are those means, okay? But if we want to be fully Bayesian about our approach to adjustment and looking at that bias measure, we also need all those variances and covariances. So you see the variances on the diagonal and the covariances of these variables off the diagonal. These are these weighted estimates using the ACS weights. That's the aggregate information that we need to input to the subsequent estimation procedure for the SMUBs. Okay, just want to make sure everybody's clear on this point. This information came from a separate weighted analysis performed outside of the RStudio file. Okay, so we're going to separate those then into the mean vector, okay, for the non-selected cases, and the covariance matrix for the non-selected cases with this code here. So this code is just pulling out the mean vector and the variance covariance matrix for those non-selected cases because we need those as separate inputs. So I'm going to run that chunk. Okay, so it's really just kind of a data management thing, but you can see the names of all the variables in that subsequent file. Okay, from that step here. So
Hey,
we have
Brady,
yeah.
Hey, Brady, can you make the console part smaller? Because it's just duplicated. Yeah, just drag that down. We don't really need it at all, I don't think.
Yeah, I'll just put it.
And for the benefit of the people looking at this data frame and wondering why it is in this funny format, this is just the way that it came out of SAS, right? So SAS was used to get these variance, covariance, and the means, and the output from SAS is the output delivery system from SAS produces this thing where there's a row with the means and the covariance matrices beneath it. So that's just unique to the fact that these estimates came from SAS.
Yeah, we're going to go through this same process of calculating these weighted estimates like manually in subsequent examples. This was just given all the different variables here. We want to get this from ACS. So, okay. All right, so now we have those extracted. Now we have all the necessary inputs that we need to calculate that SMUB index. We have the observables from our non-probability sample. We have these population aggregates on all the harmonized Z variables. Now we're ready to move forward with the calculation of the SMUB index. Okay. All right. So the functions that make the SMUB calculations available are up on GitHub right now. Okay. So this chunk is just sourcing in the R code that's up on GitHub in a publicly accessible space to implement that SMUB methodology. All right. So this is an essential step. I think Rebecca's still working on an R package that's going to put like all this stuff in one place. But right now we have our stuff up on GitHub. So that's kind of a longer term project. But for now, we're downloading and sourcing that the R functions that are required for the SMUB calculation. So when I run this chunk, nothing's going to happen, but we now have those functions available, okay, for calculating the SMUB measures and the subsequent adjustments. Specifically, the two functions that we're going to use are this NISB, which gives us those kind of plug-in maximum likelihood estimates of the SMUB and those endpoints of the interval. And then NISB Bayes, which implements that fully Bayesian estimation of SMUB. And we can use that for corresponding adjustments, where we get many draws of the SMUB for different choices of phi, reflecting uncertainty and all the estimation that underlies this. And yeah, NISB comes from non-ignorable selection bias. That's what that stands for. Okay. All right. So step 3A, as we said in the slides, Bayesian estimation. So first, we're going to implement this Bayesian approach. We're going to put a uniform 0-1 prior on phi. So that says we don't know anything about phi. We're going to start the fully Bayesian approach with draws of phi from this uniform 0-1 distribution, and subsequently take draws of all the other parameters defined by that pattern mixture model, which, remember, we can identify the necessary parameters once we have a choice of phi. Okay, so it's important to start with those draws of phi. Okay, then the SMUB functions take as input all those summary statistics. So we calculate those same summary statistics for the selected sample, and we put them in a list format for the SMUB functions. Okay, we're treating the census HPS sample again as the non-probability sample. So in the SMUB calculations, we're ignoring the sample weights. All right, so that's also important to say. We're using the raw data from our SMUB or for our SMUB calculations coming from the non-probability sample as is. Okay, so to get the full matrix of those z variables, we're kind of taking a shortcut here. We're running a linear regression model to create that proxy variable x. But what that also allows us to do is get the design matrix of all those variables out of that particular linear regression. So this is the part that I mentioned earlier, not a trivial process, right? You might spend some time building that proxy, right? We're trying to find the best possible predictor of that y. In this application, we're just plugging in the so-called main effects of all these different covariates. So if you look at this formula object, PHQ4 is the dependent variable, then we just list all those binary indicators separated by pluses. So we're not looking at interactions like we talked about earlier. We're not doing anything more fancy than fitting a linear regression model. You could use whatever complicated methodology you wanted really to form these variables that are used to predict y, as long as you can get those same predictors out of your population source. That's the key thing. So we're being straightforward here, but there's a reason to do that because we also want to get the same z's from our population source. So if you form an interaction term, you also have to create that interaction term for your population source and look at its mean and look at its variances and covariances with the other z. So there's a reason that we're being relatively simple with the model specification here. But in theory, you could extend the modeling to many different types of approaches. Okay. All right, so we fit that linear model, and that's what allows us to get the proxy variable, which again is just the predictions of PHQ4 based on the model that was fitted to the non-probability sample. So we can look at the strength of the proxy. Here, we're just getting the square root of r squared from that fitted linear model. That's all this chunk is doing. And when we do that, I got to run the model first. Hold on. When we do that, we find that r squared value is about, or I'm sorry, the r value is about 0.283, right? So empirically, we found that values of 0.3, 0.4 for the correlation between x and y generally perform pretty well. This is dropping a little bit below what we've seen empirically to be pretty effective. So remember, we want that auxiliary proxy to be a good predictor of y, Here, again, that R is about 0.283. So a little bit weaker, not great. We're going to see some stronger proxies in the later examples. But this reiterates the point we've been making. If the Z variables that you have are largely just demographics, they may or may not do a good job of predicting whatever Y you've chosen to analyze. And in this case, kind of moderate. Okay. Right. And this is the maximum likelihood estimate of the proxy strength. Again, we could use kind of a cross-validated approach. All right. So now we're going to create a list of those summary statistics for the selected sample, okay, based on that again, the design matrix from the regression model that we just fit. That's where we're getting all of the different variables that we're using in the design matrix for the selected sample to create this list. And then see, for example, part of this, we're just looking at the straightforward mean of Y for the selected sample. That's one of the inputs. Okay, that's a necessary input to the SMUB procedure along with the design matrix of the model that was used to build the auxiliary proxy. We're getting the covariance matrix of the Y's and Z's for the selected sample. We need those covariances to be Bayesian. Normally, we would just need the means, but we need those variances and covariances for the fully Bayesian approach. We're going to get our sample size for the selected sample, and then we're going to save all this information in a list. The means of the Y's and Z's for the selected sample, the variance covariance matrix of the Y's and Z's for the selected sample, and then the size of the selected sample. Okay, all of that is being saved in this list that's called stat selected. That's an input to the NISB functions. All right, so I run this whole process. That gives us all the essential information. So before we move forward, we want to look at the components of that list that are going to be sent into the NISB functions. Okay, so first, the vector of means of the Y's and Z's. Okay, that's all this chunk is doing, is looking at the vector of means for the Y and Z variables based on the selected non-probability sample. And so that's all this output is showing you here are just all those means, okay, for the different variables that are being used, including the indicators for the different states. Okay. Next, the covariance matrix for the selected sample of the Y's and Z's. So this is going to be 64 by 64. We're just looking at the first 5 rows by the first 5 columns for ease of visualization. But you can imagine the larger 64 by 64 matrix that's represented by this object here. So this is just showing, again, variances and covariances of all these variables based on the selected sample. All right. Then finally, the size of the selected sample. Again, as we saw earlier, 64,588. All of these are inputs to those SMUB calculations. Okay. Now we create that same list of the summary statistics for the non-selected sample. This is all that stuff that we just computed from ACS. So the weighted means for those non-selected cases, the weighted variances and covariances for the non-selected cases, and then the size of that non-selected sample, that's entirely approximate. We're just describing basically the size of the remaining US population of adults, okay, with that number there, which is 250 million, okay? All right, so since the sampling fraction is so tiny, that does not have to be an exact number for the size of that non-selected sample. It's not really going to affect your overall results. So that chunk is creating the same list of the same information on the Z's for the non-selected cases, not the Y, because we didn't have Y within the ACS. So now again, we look at these, the vector of means on the Z's, okay? That's what this stats non-selected is going to give us. Not pretty, it's just a vector of means on all those Z variables. We can line that up with the same vector of means on the Z variables for the non-probability sample, okay? Next, the covariance matrix of all those input Z variables, okay? Again, not pretty. We're just looking at the first 5 rows by the first 5 columns, okay? Again, you could line that up with the same Z's for the selected sample, okay? Remember, these are weighted. These are population estimates of these variances and covariances. And then again, the size of the non-selected sample, which is just a large number given the small sampling fraction. Okay, now we have all the stuff that we need to input to the NISB functions to calculate those SMUB measures, okay? So let's take a careful look, and we've tried to comment. The comments are being kind of realigned here, so I'm going to move this a little bit. Okay, so we've tried to add comments for each input argument to the NISB base function, so you know exactly what's being input here, all right? So the function's NISB base. First argument is the statistics for the selected cases. That's just the stat selected case list that we just created. Next argument is the statistics for the non-selected cases. That's the stats no selected list that we just created. The number of draws that we want from the posterior distribution for SMUB. Okay, that's arbitrary. We said we want 1,000 draws of that SMUB index from the Bayesian approach. Okay. The prior for the sensitivity parameter phi. That's that uniform 0-1 prior. We want to take 1,000 draws of that phi from that uniform 0-1 prior. Okay. If we want plug-in estimates, okay, what values of phi do we want to choose? 0, 0.5, and 1, arbitrary. Okay, we want to see values of the SMUB at those specific values. Credible intervals we want to compute using 0.95. Okay, that's just the type of credible interval you want to compute. A random seed if you want to be able to replicate the Bayesian approach. Okay, arbitrary. The functions will also plot the drawn values of the SMUB index as a function of phi. Okay, so you can add a plot that will be created in real time to show you the draws of SMUB depending on the choice of phi. Okay, and then a couple other miscellaneous options just to control the nature of the overall plot. Okay, so those are, you can rely on defaults typically for those. Okay, now this is kind of the meat of everything we're talking about. So the NISB based function, depending on your application, might take a while to run. Okay, because we're asking for 1,000 draws. So this chunk, I'm going to go ahead and run it, but it might take a little bit. Okay, here, insanely quick. So the fully Bayesian approach just took milliseconds. Okay, to do all the 1,000 draws based on the pattern mixture model, given the input information, all the calculations of SMUB, all that being done repeatedly, already done. Okay, and we're fully Bayesian about it. So we're accounting for all those sources of uncertainty. Here is that plot that we asked for. Okay, so this is showing, remember, we had 1,000 draws. So at each drawn value of phi from that uniform 0-1 distribution, we don't know anything about phi. It could be anything between 0 and 1. We're just allowing for that draw. For each possible draw of phi, you see the range of possible computations of SMUB, draws of SMUB from the posterior based on the pattern mixture model. And you can see for any given value of phi, there's a pretty tight range of drawn values of SMUB. We get a good idea of what that SMUB value is for that value of phi. And remember, the SMUB is the bias estimate. It's not the adjusted estimate. It's the amount of bias in that estimate. And you can see on the y-axis, all these drawn values are negative, and nothing's really coming close to 0. That's telling us that our non-probability sample estimate is very likely biased low compared to the full population estimate. And that's consistent with what we speculated going in. We said it's probably the case that people with better mental health are the ones responding to the household pulse survey. Okay? So again, stopping early with a design-based approach, this is what that assumption of ignorability is missing. And this is telling you it doesn't matter what value of phi you're willing to assume. All of these values of SMUB are negative. And if phi is higher, the closer phi gets to 1, more bias. Okay? The stronger the non-ignorable selection mechanism, the more bias in the estimate. Okay? And on top of that, you're getting this range of uncertainty from the fully Bayesian approach, which you can see is pretty tight in this particular application. So we have a pretty good sense of what's going on. So this is, again, just showing all the posterior draws and showing this constant negative value of the SMUB index for this particular estimate. Paul, yep.
Yeah, I have a question about the prior distribution on the phi.
Yeah.
So I noticed you're usually using this uniform 0-1, but do you have an intuition around when you might depart from that and use a different distribution? Or
yeah, so Rebecca gave a presentation actually on some of her related research with one of her students, and generally you might want to refine like the information that you have on phi based on earlier investigations. So she did an earlier investigation where she had access to the truth, the value she was trying to compute, and she found that choices of phi like between 0.4 and 0.6 would give you a reasonable idea. So again, 0.5 generally seems like a good choice of phi, given applications that we've looked at so far. But typically, this is, again, the full range of possibilities. You might refine that or use a different prior altogether based on what you've learned from previous studies. Okay, it's usually if you're just getting started and you have no idea what phi is from the data, this is a reasonable choice. But the more applications that you look at, you might want to refine that. And then you get a tighter set of draws. Yep. I don't know, Rebecca, if you want to add anything to that. So
Yeah, I think that a uniform prior is, so first of all, let's be clear, as Brady has said repeatedly, there's no information in the data about fees, so your results are entirely driven by the prior, right? The prior, what you see is because of what you chose the prior to be, basically. So a prior of a uniform 0, 1 is equal, is saying it's equally likely that we have totally not ignorable as ignorable. That's it's a strange prior in the sense that we probably don't believe that. We probably believe it's something more moderate. So you could put some kind of a continuous prior that sort of had heavier weight on the lower values of phi and then tailed off and less on the 1. And that may be desirable because, as you can sort of see in this plot, although this is a very big sample size, so it's not totally obvious, variability of these estimates grows as phi gets closer to 1. So with smaller data sets, you often will see that the precision at the higher values of phi, it becomes very, very noisy anyway. And so you may want to kind of downweight those, but you're going to see the same pattern of of the results as a function of phi.
Yep. Okay. Yeah, that text kind of summarizes what I was just saying. Now, given the draws of SMUB, we can look at those 95% credible intervals for the actual bias index. Okay. So that's what this next piece is doing. It's just looking at the overall marginal posterior median and then the 95% credible interval for SMUB. So that's how you can kind of extract that overall inference about this particular estimate. So you can see the median of those draws is about negative 0.6 for the bias estimate. And then it ranges between negative 1.9 and 0.2, or negative 0.2, excuse me. The key point being here, that 95% credible interval based on the fully Bayesian approach does not include 0 as a plausible value. So here, if you're trying to make inference about whether or not that non-probability sample estimate of the mean is biased, the inference you would make here is, yes, there's evidence that there's non-ignorable selection going on here based on the draws of the SMUB. Okay. If that interval included 0, then you're less concerned about bias, and maybe the standard weighted approach or even ignoring the weights would be a reasonable choice. But here, there's pretty clear evidence of non-zero negative bias in the estimate of the mean. Okay. You can also look at the draws, again, for those specified values that you input to the function. So if you want to see draws at associated with 0, the draws associated with 0.5, the draws associated with 1, you can get these conditional draws of the SMUB. And what this analysis is showing you is just the same 95% credible interval for the bias under each of those assumptions. And this is just reiterating my point that no matter what value of phi we selected or we're willing to assume, that 95% credible interval is still negative. Okay, so at no assumed value of phi is there evidence that there's no non-ignorable selection. It definitely seems like an issue with this particular mean. And again, all of this is just for one mean. We'd want to repeat this for all the other estimates that we're looking at. Okay? So that's fully Bayesian. And again, the nice thing, and that's why Rebecca and I kind of endorse the fully Bayesian approach, is that these credible intervals are accounting for all those different levels of uncertainty in the calculation of the SMUB index, all the estimation that's going into that calculation outside of the population parameters, like we've been talking about. This fully Bayesian approach accounts for that and allows you to put a prior on phi. We just need those variances and covariances of the z's to pull this off. Okay, Paul's question.
Yeah, we got a question from the chat. Oh, Rebecca just answered this one, but I'll read it anyway, just in case you want to add something.
Okay.
Does the non-weighted estimates from the pulse affect the interpretation of the SMUB? Is it no ignorable bias relative to the unweighted estimate? What if the weights partly take care of that?
Yeah, so that's a great question. There's another piece of this in the original paper where we talked about this called the SMAB. So we've been focusing on the SMUB, but you can also do these calculations showing you how much bias remains after a typical weighting adjustment, assuming ignorability. So these functions also enable a SMAB calculation that say, even if you were to apply a weighting adjustment like we saw earlier, getting that estimate up to 3.1, how much additional bias appears to be left after that initial weighting adjustment. The definition of the SMUB is saying how much evidence of bias is there in the unweighted non-probability sample estimate. And so to be truthful, when I'm using this kind of application, my primary focus is on the ultimate adjusted estimate. Okay, this is a bias measure relative to the fully unadjusted, non-weighted, non-probability estimate of the mean. I want to see that final adjusted value. So what that final adjusted value is going to give me is, even if some of that selection is ignorable, the overall adjustment being implemented here is accounting for all of that, ignorable and non-ignorable, and adjusting my estimate accordingly. So even if the weights are fixing up some of the bias, we want to fix up that additional piece that's due to non-ignorability, that phi times y part. This is accounting for that. So
Yeah, and
yeah, go ahead.
the setting phi equals to 0 should be, it's ignorable, and it should be returning estimates that are similar to the weighted. So we can look here at this table that's on the screen. The median when phi is 0 is about negative 0.16. So that's the amount of the bias from the unweighted to the weighted. Right. So that's the amount of bias that would be removed essentially by using the weights. And so then in order to think about how much bias is there relative to the weighted, you would think about comparing to phi equals 0. Like how different is phi equals 0.5 to phi equals 0. And that's actually exactly what that SMUB estimate that Brady was talking about does.
Yep. So it's like the standardized measure of adjusted bias. That's what we were talking about. So, yeah. Okay. So step 3B is, I don't want to call it trivial, but it's much simpler than the fully Bayesian approach. We're just plugging in the specific values of phi. And to do this, we only need means, okay, to do this kind of calculation. So the NISB function by itself without Bayes is just taking the mean of the proxy X in the population, which we're taking, we obtained that from the Bayes output, the stats for the selected cases, and then the values of phi where you want to see the calculation of the SMUB. So this is just a plug-in calculation of these SMUB values at particular choices of phi. So I can run this and then look at the point estimates from that SMUB MLE object. And you can see that the MLE estimates, just by plugging in 0.5 and 1, like we had on one of those initial slides, just taking those formulas, plugging in values of 0.5 and 1, very, very close to what we saw in the fully Bayesian approach, where we had a 95% credible interval. That full range of possible bias values goes between negative 0.17 and about negative 2.09. And that 0.5 choice is about negative 0.59. The median based on the Bayesian approach was negative 0.60. So in some computation heavy cases, just using the simple plugins of the maximum likelihood estimates could give you very similar results to that fully Bayesian approach that might take a while to run. That's this particular application, but we arrive at very similar results with those simple plug-in estimators without having to need those variances and covariances of the z's, just plugging in the standard formulas. Okay. And then, like I mentioned, you can calculate the adjusted means based on the SMUB. And again, like I said, that's what I really like out of this whole method. SMUB gives you a measure of bias, but you can take that bias measure and use that to calculate an adjustment to your unweighted non-probability estimate. So that's what this step is doing down here. We're taking in the code the simple unweighted mean of y from the non-probability sample, and we're subtracting selected quantiles based on the Bayesian draws. So we're selecting the median overall, we're selecting the 0.975 to get a lower bound for the adjusted mean, and we're selecting the 0.025 quantile to get an upper bound for the unweighted mean. All this is from flipping around that formula for the SMUB to get back to the overall population estimate. Okay, so we're just subtracting the quantiles of those draws. And again, we're multiplying by the standard deviation of y, because remember, SMUB is standardized by the standard deviation. So I'm not just calculating that difference, I also have to multiply that by the standard deviation of the original y's. All right, so that step, if my goal is to make inference about the mean incorporating the adjustment, this is where I get now a posterior median draw of 4.82. Remember what the weighted mean was. It was like 3.17. Okay, this is how far off we were. Okay, this is the adjusted point estimate that we would want to provide based on the household pulse survey. And you can see how far removed that is from 3.16, what the weights weren't fixing. And you also get a 95% credible interval for that particular mean, showing the range between 3.4 and 9.2. So if one was to do an unweighted analysis or even a weighted analysis of the HPS, and their goal was to make inference about the level of anxiety and depression in that population of US adults in April 2021, based on the weighted analysis, they'd say, it was about 3 out of 16, really tight range because I had a huge sample. Not much to worry about, right? Absolutely not the case for that finite population inference. Okay. A lot of non-ignorable selection bias, and this SMUB adjustment fully adjusts for all of that potential selection bias and gives you an idea of the uncertainty as well, based on the fully Bayesian approach. Okay. So we would radically change our inferences based on that kind of approach. And keep in mind that this adjustment, we see a lot of uncertainty, right? 3.4 to 9.2, largely because of the fact that the proxy is weak. The stronger that proxy becomes, the tighter that 95% interval for the mean is going to become. The better the adjustment, the more precise the adjustment. Okay, so if we find a better proxy, better Z's with population data available, we could get even tighter 95% intervals for that adjustment. But here, there's clear evidence of non-ignorable selection bias. Okay, now we don't have a truth, right? But in our later examples, we are going to have a truth. And we're going to show you how these adjustments in many cases will get us closer to the truth when there's a known result available. Okay. Okay, so that's what we want to go over for this first example. Rebecca, anything you wanted to add before we turn back to the slides here?
The only thing I'll say is I see another question in the chat. Can you make the bias worse by a poor choice of Z?
Yeah.
So a poor choice of Z would be, I guess, a Z that's not very predictive of the outcome. And in that case, you're just going to get these very, very wide intervals. It's not as if choosing one Z over another is going to point the bias in a totally different direction.
Right. Right. Because remember, that correlation is going to be positive because you're using a linear predictor. It's just that if you have that, remember, it's kind of an inverted form for that scaling factor. The smaller that correlation becomes, just the noisier the draws become. There's going to be wider intervals. Yep. But it's going to give you a sense of the same direction. Okay. Other questions in the room or on Zoom? Yeah.
Just go a little bit on your code there.
Yep.
On the there, or compute the maximum likelihood.
Yep.
Later. You're just like, you don't have to use the output of the SMUB.
Shortcut. Yeah, that's a shortcut. If you know what the regression equation is and you know what the means are, it's just a linear combination. That's all it's doing, is just that was being computed as a part of SMUB base, so we're just grabbing it. But you could do that calculation given the regression coefficients and given the means on Z. That's literally a scalar. Yep. Any other questions about the code or this example?
Yeah, one just came through. When a main goal of an analysis is associations / prediction associations versus prevalence or mean estimates, is there a multivariate SMUB process, or does one rely on provided analysis weights?
Oh, that's example 4.
Nice, good work.
An entire separate paper was about how to do this when your goal is a regression coefficient. Yep. So we'll get there. It's a great question, but we'll get there. Yep. Other questions about example 1? Okay, if not, I'm going to turn back to the slides and drive. There is a summary slide here, just kind of wrapping up everything that we talked about with example 1. And this is just kind of the main takeaway points from that example. But hopefully everybody gets a sense that this is very doable using this code. There are certainly steps you have to be careful about, like harmonization and calculation of weighted estimates, but certainly doable. And like Rebecca and I said, we're always happy to consult on this kind of stuff because we want to make sure people are using this. Like, we really think it's powerful stuff and we want to make sure people are using it. So, okay. I'm going to turn it over to Rebecca then, who's going to start talking about proportions, which, like I said, we'll go a little bit quicker because very similar ideas. So let me make this bigger. Okay.
All right. So now we're going to turn to the situation where Y is binary instead of
Yep.
being continuous, but we are still in the same situation where we have to have a set of covariates that are observed in your non-probability sample, and you still have the margins in the population. The only thing that is changing is the nature of our Y. So in order to model the binary Y, we use a probit model with a latent variable motivation. And this is a computationally convenient thing that lets us apply the proxy pattern mixture model. So with a latent variable, we have this variable we call U that we never observe that has a normal distribution, and an individual gets a Y equals 1 when U crosses a threshold arbitrarily chosen as 0, and it's a 0 otherwise. So you could think of this as the latent tendency to have Y equals 1. And the reason that we do this and that we choose this latent variable approach is we can then take U, this normally distributed latent variable, partner it with a proxy variable, and apply the proxy pattern mixture model. So all the equations look the same, except everywhere there's a Y, there's now a U. And there's a few other details we'll talk about, but that's really the main idea is we're just replacing the continuous Y with a latent U to model a binary observed Y. Because of this latent variable, we do need a little bit more data. So Brady was showing you how you could just have means to calculate for the target population. You need variances when you are in this binary world, even for non-Bayesian estimation. So what we suggest is if you, for some reason, only have means of those Z variables in the population, you could just make the assumption that the covariance matrix of those Z's would be the same as what is in your selected sample. So often we do have estimates of variances because we're getting these estimates from something like the ACS, where we can compute means and variances like you saw in the example we just went through. So now we have a non-probability sample with our binary variable of interest. We still have the Z covariates. We still have the aggregate population information for Z, so nothing there has changed. What changes is how we make the proxy in the sense of what model we use, what regression model we use to make the proxy. So instead of a linear regression of Y on Z, we're using probit regression. So probit regression is a lot less common than something like logistic regression, but it is mathematically convenient because it has this assumption of an underlying latent variable, which is then going to plug really nicely into our pattern mixture, our proxy pattern mixture model. So this latent variable U is, you can think of it as it's going to be the prediction out of this model. It's like our U hat is what is going to be our proxy. So the probit regression here is shown on the slide. The probability Y equals 1 is now what we're modeling conditional on Z for the selected sample. We still get regression coefficients. They're denoted with alphas here. So I can still get out an estimate of the proxy by plugging in my Z's times my alpha hats. And I can still get an estimate of the mean proxy at the population level by plugging in Z bar into that regression equation. The proxy strength when there is a binary Y is a little bit different. So instead of just being a standard correlation, we're now talking about the correlation between a binary Y and a continuous X, making the assumption of a latent variable underlying the Y, and that's something called a biserial correlation. So it is an estimate of the correlation between the latent U variable and the continuous X proxy. So we'd call that rho, just like we did for the continuous Y, is just the subscript. Again, the U is replacing the Y. So just like with the model for continuous Ys, there can be those other covariates V that are independent of X and Y, and otherwise it's the same model, just with a U in place of a Y. So we have a continuous U, a continuous proxy. We apply the pattern mixture model. There's one additional constraint. When we have a latent variable, we cannot separately estimate the mean and its variance, so we fix the variance of that latent variable for the selected sample to be 1. This is a very standard assumption. We make that same assumption about selection as we did when it was continuous Y, but now U replaces Y. So this is a little bit weird to think about because we never actually observe U. But instead of thinking about it as there's a propensity to respond for the Y equals 0 people and the Y equals 1 people, now there's a continuum of the propensity to respond depending on how large or small your underlying latent variable is, regardless of whether you've crossed the threshold into being a Y equals 0 to a Y equals 1. So we have the same sensitivity parameter phi here, where the probability of selection, of self-selecting into the non-probability sample is a function of this linear combination of the observed proxy X and the latent variable U. And we do the exact same varying of phi. Phi equals 0 means ignorable, phi equals 1 means extremely non-ignorable, and the likely true value is probably somewhere in between in some sort of moderately non-ignorable scenario. So I'm going through this relatively quickly because it's the same, right? We're introduced this latent variable trick. So one thing that is different is that probit models and latent variables are a little fussy when it comes to maximum likelihood estimation. And you could do full maximum likelihood estimation and return back your estimate of the mean of Y and your selected sample not equal to the observed mean of Y. Right? This is just the way the likelihood works. So that's an unattractive quality. We would rather have an estimation method in which returns Y bar for the estimate of the mean of Y. So we use something that we call modified maximum likelihood, which is essentially a two-step process where you sort of fix that mean of Y to the observed value and then estimate the other components. This is very standard. We did not invent this, the two-step estimation method. So what do we actually care about? We care about a mean of a binary variable. And so how do we get that? It is a weighted average of the mean of Y that's in your non-probability sample and the mean of Y that is in the rest of the population, the non-selected sample. So that's what the first part of this equation is showing you. It's for a given value of phi, my overall adjusted value of Y is going to be a mean in the non-probability sample times pi, which is the selection fraction, plus the mean in the rest of the population times 1 minus pi. But the mean of Y, because we're in this latent variable framework, is the probability that U is greater than 0. So and since U has a normal distribution, that's a quantity that we can calculate, right? That's the cumulative CDF of the normal distribution. So ultimately, we're going to want to have inference about that overall mean, and it's just going to be a weighted average of the prediction of the mean in the rest of the population and the observed mean in the non-probability sample. So that first piece, where it's the mean of Y in the non-probability sample, that's the piece where the two-step approach is important, because if we did the fully maximum likelihood, that wouldn't be Y bar. But because we're doing this two-step estimation, this modified maximum likelihood, that will in fact just be the same thing as you would get if you took the average of that 0, 1 variable in your non-probability sample. So in the proxy pattern mixture model, making that identification assumption identifies these parameters that we wouldn't otherwise know. So you can see in the far right-hand side of the top equation, there's that mu u hat 0 and sigma u hat 0. Those are the parameters that describe the distribution of the latent variable in the non-selected sample. We don't know what those are. We have no information in the data with which to estimate those. And it's that identification restriction about selection and the phi parameter that lets us have estimates for those two quantities that's then going to let us get back to our estimate. So the estimates of those based on the pattern mixture model are shown in the bottom slide. And just like the case of when Brady was talking about the SMUB, it's about shifting. It's about taking what we observe in the proxy and the bias in a proxy variable and applying it to the latent U. Just like we took the bias that we saw in X and applied it to the continuous Y, now we're taking the bias in the X and applying it to the latent U. You'll notice that the first expression in parentheses in both of the two equations on the bottom, that's got the phi plus 1 minus phi rho on the top, phi rho plus 1 minus phi on the bottom. That's the same as it was in the continuous Y model. There's just a U. And actually, those all have typos.
That should be UX.
Those should all be UX. Yes, the U should have replaced the X, not the Y. We can fix that.
Sorry about that.
Yeah. But it is the same, right? So this idea of how much the shifting and scaling happens is really tightly related to that correlation, which here is a biserial correlation, right? The relationship between the binary Y and the continuous X variable.
Yep. And key thing I want to emphasize here is, again, to do that calculation where we're getting the overall mean of Y, we need not just the adjusted mean of U for the non-selected cases, but also that adjusted variance piece. So we're looking at both types. What we saw is like a SMUB type adjustment. We're looking at that for both the mean and the variance of U. So that's important to recognize here. We need that additional piece in this binary case.
So from this equation for the estimated overall proportion in the population that depends on phi, we can take that and just subtract off the observed in the non-probability sample to get a measure of bias. So this one is the MUBP, which I don't think you can say out loud the way you can say SMUB, but it's really simple to interpret because we're talking about proportions, so we don't need to worry about standard deviations. We don't have to standardize anything. The bias here is going to be the bias in your estimated proportion relative to what the model predicts is true in the population. And again, as to the earlier question, this is all about the unweighted estimate. That mu hat y shown there, or the first one, the non-probability sample mean, that's the just raw average y bar in your sample. So it's simpler to interpret in that sense, meaning it's easy to compare across y's. So if you had lots of y's, you could see what is how much bias, how many percentage points bias is the model predicting, and compare across the y's. For continuous y, you have to do that standardization by a standard deviation to be able to compare across outcomes.
Yep, and this also shows too, with this very simple expression, if we want a good estimate of the overall mean of y for this binary variable, we just flip that around and you get that estimate by subtracting the MUBP from the mean for the non-probability sample. It's just a very simple adjustment to get that overall mean that you're probably interested in. So very straightforward.
So I already mentioned that we're not actually doing true maximum likelihood estimation. We're doing a modified maximum likelihood estimation, and that's so that we can get the estimate of the mean of y in the non-probability sample that we want. Otherwise, it's not going to be exactly y bar, and that's a little bit weird. If the assumptions that underlie the model are truly hold bivariate normality, then you would in fact return essentially the same estimate. But if there's any kind of skewness, it will return a mean of y in your observed sample that's not exactly your observed mean of the 0, 1 variable. So in addition to doing this modified maximum likelihood estimation, as Brady showed and sort of emphasized, we like to be Bayesian, you can do a Bayesian estimation just like you can for the SMUB, and you can have credible intervals. Put a prior on phi, uniform 0, 1, or something else, and look at the effect of varying phi on the inference. And just like with the SMUB, if you want point estimates, the phi equals 0, phi equals 0.5, and phi equals 1 are sort of a good set of estimates to bound the potential for the non-response bias. So one main difference in implementation that you're going to see in the R code is for the SMUB, we turned everything into summary statistics, right? The selected sample, the non-selected sample, everything was summary statistics. But the functions to calculate the MUBP need the microdata from the non-probability sample. And this is because we're running a probit model. So we need the microdata to run the probit model because there's no closed form solution for those beta hats. In linear regression, I can give you those estimates, the beta hats for y given z, with just sufficient statistics. I can just have means and variances and covariances, and I can tell you what those beta hats are. That is not true for the probit model. So the input into the function has to include your selected samples y's and the z data. So it's a different input. For the summary statistics for the population, it's still the summary statistics for the population. So another difference is that you have to have covariances. So because of this probit model and the latent U, we need covariances. So we may have to take shortcuts about the population if we need to assume it has the same covariance as the observed data if we don't have that information from the population source. So in some simulations that we've done, we've shown that the MUBP outperforms the SMUB for binary y's. So of course you could pretend that y is continuous and you could use the SMUB, but it's going to not do well with variance estimation, as you would expect, given the mean variance relationship for binary variables. And so the MUBP is the preferred inference option if you in fact have a binary y variable. The SMUB can do things, as often happens when you treat a binary variable as a continuous variable in, let's say, a regression model. You can get predictions that give you estimated proportions outside the bounds of 0 to 1. So that's undesirable. But the MUBP, because it is treating y correctly as binary, will never give you estimates outside of the 0, 1 interval. So the necessary conditions for using the MUBP, this is a pretty similar looking slide to the one about the SMUB. You need those covariates to be moderate or strong predictors of Y in the non-probability sample. And I will say that people ask me about this often, like, how do I know? How do you pick them? And usually my response is, it's what you have. Like, I find myself in scenarios most of the time where I don't have a lot of options. I've got mostly just demographic variables that I have that I can use to be predictors. I don't have the luxury of having a rich population source from which to choose which are my good predictors. There may be some scenarios in which you have a sampling frame or other population data that is much richer, but in a lot of the applications I see, it's like, well, I hope they're moderately strong because they're the Z's that I have. So you need that population level aggregate data for the covariance, for the covariates. And again, you need the means like you do for SMUB, but you also need that variance covariance matrix. And then as with the MUBP, or as with the SMUB, you have to be able to clearly define the target population. And so we're going to show two examples with this binary, one where we have the easy scenario, an easily defined population, all US adults 18 plus, and a much harder situation, a dynamic population of likely voters in a US election, where even obtaining those marginal population level summaries is really challenging and there aren't great data sources. So now on to our second example. This is estimating the proportion vaccinated for COVID-19 based on the Census Household Pulse Survey. So the good news here is we're using the same data set as the first example in terms of the data source. So it's we don't need to do as much explaining. So these are the Census Household Pulse data that we used for the continuous Y variable, but now we're using a binary Y variable, and it is COVID-19 vaccination status. So it's the same Census Household Pulse survey with that tiny 7.5% response rate that we're concerned it has led to substantial selection bias. So the goal is to estimate the proportion of adults in the US with at least one dose of COVID-19 vaccine. And importantly, this wave that we've chosen corresponds to vaccines being available to everybody for about a month. So anybody could have had a vaccine in the time frame of this survey. But our concern is that people who were unvaccinated may have been less likely to participate in this government-sponsored survey. The survey was not technically about the COVID-19 pandemic. That's not how it was sold, but it was a highly politicized climate, and individuals who were distrustful of the government, distrustful of a vaccine from the government, may have also not opted to say, sure, I'll take this US government-sponsored survey. So we believe that there is the potential for some non-ignorable selection bias. So same data source. This is a non-probability sample for the same reasons as the first example. We do have a larger sample size here, about 78,000 individuals, and that's because we are making the assumption that there is no missing data for the vaccination question. And by that, I mean there is a small number of individuals in the sample who did not answer the vaccine question, and we assume that they are not vaccinated. And this is in line with the way the census was producing estimates out of this survey at the time. So small number of people who skipped this question or said, I don't know, we code them as a no. So therefore, this 78,000 is everybody who responded to the Census Household Pulse, no missing data. Unlike the PHQ, right, the depression score, where there was this almost 20% of individuals who answered other questions in the survey but didn't answer that question. The covariates we're going to use, we'll make it simple. We'll use the same ones as for the PHQ-4, sex, age, education, race, ethnicity, and state, coded in exactly the same way. And of course, again, we have those Census Household Pulse survey weights where they rate to the ACS margins, exactly as we had in the previous example. So once again, we're going to look at four different things. The unweighted estimate of the percentage vaccinated, which, as Brady said, nobody should ever be using, but sometimes people do use. The weighted estimate using the Household Pulse survey weights, the MUBP index of selection bias, so that'll be an estimate of that percentage points of bias for the unweighted estimate, and then an estimate of the percentage vaccinated where we use the MUBP to adjust. So we basically just add that bias, right, to the unweighted estimate. So again, this interpretation of the MUBP is a difference in proportions, what I observed in my sample versus minus the population estimate under this model for a particular phi value. The population source, we've got the same target population, all adults age 18 plus, stable, well-defined, same summary statistics. In fact, you're going to read in the R code the exact same data set that was created in SAS that has the means and the variances. So we did not make any attempt to play around and get a different set of covariates. So in this particular instance, however, vaccination status was shown to be actually decently predictive, or decently well predicted by demographic information. And so, in fact, we're going to see a stronger proxy. So these demographic covariates are actually better at predicting vaccination status than they are at predicting depression score. One thing that's different about the PHQ-4 score and that makes this a really exciting example is we have a benchmark truth. So we have this retrospectively available information from the CDC of the true proportion of US adults who were vaccinated in the United States. And this does include retroactive corrections that were done to this benchmark data. So we know from this CDC data source, the true proportion is 61.4%. So that's great because we're going to be able to look and see whether the MUBP adjustments are going to capture that, right? Whether we're moving in the right direction and whether our method sort of would have predicted or shown the direction and magnitude of the bias. So as a spoiler alert, and some of you may know this from having heard this, and so even the popular media had it, the estimates of vaccination status that came out of the HPS were very badly biased. Right? Even the weighted estimates were drastically overestimating the proportion of US adults who were vaccinated. So it's interesting to see whether the MUBP can in fact correctly detect the direction and the magnitude of bias. And in fact, the reason we ever did this analysis in the first place is because I read the article and saw the headlines about the drastic overestimation. And I said, that's non-ignorable selection. But that's got to be what that is. That's because the people who participated were fundamentally different with respect to vaccination status than the people who did not participate. So the roadmap for example 2 looks very similar to what we did for example 1. Calculate the estimates from the selected sample, both unweighted and weighted. Get the summary statistics for the non-selected sample. As I already said, it's going to be the same as we used in the first example. Calculate the MUBP index, both being Bayesian and using those modified maximum likelihood estimates, and then calculate adjusted proportions based on that bias index. So if you are playing along at home, I want to point out that the code that does the Bayesian implementation, so when Brady did it for the continuous Y, he went, oh, it happened in a microsecond. It does not happen in a microsecond for the binary outcome, especially not with this large of a data set. So this code is not optimized for large data sets or anything, so it will take a minute to run when we get to the Bayesian part. All right, so a lot of this is the same at the beginning. It is a different data set just because instead of the PHQ score, it's the vaccinated variable, and it's a larger data set because there are additional rows relative to the first one because this is all of the people who participated in HPS, but the data manipulation that's happening here is identical. All right, so look at these are the same variables, the weight, gender, education, etc. Here, vaccinated is the variable that I have created. And just to the left of it, you see this household pulse variable. It's this received vaccine variable that takes the value 1 for yes and 2 for no. And there are negative 99s in there for the don't know. They get coded to unvaccinated. And I see a question in the chat. Does your analysis also work well if they were misreporting? So that's a good question. So if there is some kind of measurement error or underlying they're lying, that's not being captured in this, right? We're under the assumption that the reports of the people who participated in here are accurately reporting their status.
Yeah, all this work is really addressing like one part of the total survey error framework. It's that selection step. It's not a magic fix up for measurement error and other sources of error. So, yeah.
If only, wouldn't it be nice?
If only.
All right, so we have our data, we've got it prepped. We can do the exact same thing as we did with the continuous Y, which is get an unweighted estimate and look at its confidence interval. Again, this is a proportion. It's about 82.3%. So that's the unweighted estimate. If you remember, the truth is 61%. Estimate 82%. massively overestimated. Now, of course, this is the unweighted estimate. So let's use the weights. We know from looking at the data, we didn't show you this here, but demographically, the respondents look different than the rest of the US population with regard to demographics. So the weights that raked to these demographic margins should produce better estimates. And in fact, it lowers them. So now using the weights, we get an estimated vaccination proportion of 74%. So that's good. It's not 84. 74 is closer to 61. But it is still substantially biased, and the confidence interval is very narrow because, as Brady said, right, big data comes with this big problem of a lot of precision when there might actually also be a lot of bias. So we can see that where the weights are helping, but it's not getting us all the way there. So the idea is, can the MUBP capture the direction of the remaining bias? So once again, that second step is to go get the summary statistics for the non-selected sample. The data set that's being read in here in this example is the same one as from before, right? It's the ACS mean and covariance matrix with those dichotomized indicator variables for the different levels of the Z variable. And exactly the same code here again, separating this output that had come from SAS into a vector of means and a covariance matrix. So, and again, with this MUBP, we always need that covariance matrix. So once again, even though the household pulse is a very large survey, it is small relative to the size of the target population. So we're setting that non-selected sample size to be about 250 million, as we did in example 1. So now we can get to the fun part, which is calculating the MUBP index. So once again, we're going out to GitHub and downloading the versions of these functions that live out on Brady's GitHub. So that's all that this code is doing, is it is, yelling about packages that are not installed.
I'll install those real quick.
Fantastic. So as Brady did say earlier, I have a student who was working on creating an R package to do this so that you don't have to go out and get the separate functions, but that is not really ready for prime time yet. So at this point, using the functions on GitHub is your best bet. And I do want to point out that in addition to the code that you have here in this workshop, on the GitHub with each of these functions, there'll be these example code files that have additional examples of implementing the functions. So that are different actually from the ones that we're using in this workshop. All right, so we have downloaded the functions, and the two that we're going to use are this MLE two-step MUBP and this proxy draws. So the first one is that modified maximum likelihood, point estimates, and the second one is the Bayesian estimation function. So we'll start by being Bayes. So we'll put a uniform prior on the sensitivity parameter, and this is where the inputs to the function are different than they are when y is continuous, because we have to send the microdata into the function. So in this code here, I'm pulling y1 out, which is the outcome variable, so that I can do some manipulations with it later. And I'm putting into a variable called n1 just the sample size, that's that 78,000. And then I'm running that probit model. So with continuous y, it was a linear regression. Here it is a probit model with vaccinated being the binary outcome. Everything on the right-hand side is the same. You'll notice that I'm using the GLM function because I'm running a probit model, generalized linear model, and I specify binomial link equals probit. So that's really important because the default is going to be logistic regression. So we run this probit model, and you notice that that wasn't completely instantaneous because, again, the probit model takes a second to run. And now we have a probit model that on its sort of by itself is not actually all that useful because we don't really have nice interpretations for probit coefficients, but we don't actually care about interpretation of the coefficients of this probit model. We just want to use it to create the proxy. So before we move on to the rest of the estimation, we should check the strength of the proxy like we do in the continuous case. The problem is we can't just do like correlation y and proxy because y is binary, and I don't want the point biserial correlation, which is what you would get if you did that, a Pearson correlation between a binary variable and a continuous variable. We actually want that correlation between the latent u and the proxy. So this biserial correlation, we need a separate function to do it. There are existing functions that exist out there in other packages. This is just our version of it, where I first create the proxy for the selected sample by getting the prediction out of the regression model. So this is a generalized linear model. So I use the prediction function with type equals link, which means plug in your z's and give me the beta 0 hat plus beta 1 hat times z1, right? The prediction on the linear prediction scale, and that's x1. So if we were to look at x1, we would see it as a continuous variable with a sort of bell curve shaped distribution. Then I can take that x1 continuous proxy variable, the binary outcome y1, and feed them into this two-step biserial correlation function, and I get about 0.46. So this is the parallel to that correlation that was kind of the r squared, the square root of the r squared in the linear regression, but this is much stronger, right? 0.46 is considerably larger than the about 0.28. And again, these are pretty basic demographics that we're using, and we're doing a pretty good job at predicting who was getting vaccinated. So now we can move on to the calculation of the MUBP. So I will fully admit that Brady wrote the code for the functions in the first example. Rebecca wrote the code for the functions in the second example. So the way the inputs come, it's a little bit different. So that's what we're hoping to kind of standardize in a package version of this. So first, we take the predictors for the selected sample. So that's your microdata in your non-probability sample, just the z variables. And as a trick, we can just do model matrix on the fit object, and that's going to return us back the matrix of the predictors. That includes a column for the intercept as part of the model matrix. So the second line of code here is just taking that off. And that's because an intercept is actually added within the functions. So we don't want to send in a column of ones because the code will think that that's a predictor variable where that's entirely ones. We're being Bayesian, so we set the seed, and now we send everything into the function. And again, I have a note here that this is not a particularly efficient function. It doesn't attempt to do anything to speed up the code. It's a large sample, and it takes a couple minutes to run. So Brady can click run, and we can watch it tick while I talk about what the inputs are. So we have the outcome variable, that's the Y variable in the household pulse data set. We have the Z variables, that's the matrix of all the predictor variables, which in this instance are all these binary indicators, and the size of the selected sample. So this chunk, this piece is different than what got fed in the continuous case where we could just send in summary statistics. Then for the non-selected, we send in summary statistics. So the mean vector for the non-selected sample, the variance covariance matrix of the non-selected sample, and the size of the non-selected sample. Then the next couple of options are about the phi value. Are we fixing it to one value, or are we putting a prior on it? If you set draw phi equals true, this is going to draw from the uniform 0, 1. And so it doesn't matter what you put for phi equals. So this arbitrarily says phi equals 0, but it doesn't matter what that is. If instead you set draw phi equal to false, then you pick a value of phi and the entire estimation will fix phi at 0.5 or fix it at 0 or fix it at 1. And then the number of replicates is the last input here. I will note that we would normally want you to run more than 500 replicates, but since this is a workshop, we don't want you waiting for too long. We're just going to base this on 500 posterior draws. So unlike the continuous case functions, the MUBP functions do not draw plots, but we might want to look at a plot of the MUBP versus phi. So that's pretty easy to do because the output to the function includes the draws in a matrix. So I'm just, for convenience, turning that into a tibble, right, as a sort of data frame on steroids, and then doing a plot. So this is just using ggplot to create a plot where, again, just so the equivalent type of plot as we saw for the continuous y, where phi is on the x-axis, it goes from 0 to 1, and the MUBP is on the y-axis. And remember, that's the estimated bias in that raw unweighted proportion, which again, remember, was 82%. As phi goes from 0 to 1, it gets larger and larger, right? So there's more and more bias. It's an overestimate, more and more overestimating, the more and more non-ignorable that you go. And these are very large, right? These are percentages, right? So this is the y-axis there is from 0.1, right? 10 percentage points all the way up to 0.45. So there's evidence that there could potentially be a lot of bias in this estimate. So this index is positive, which means we're overestimating it, which we already know because we have the truth. Again, in this plot, like in the other one, very tight cluster of the points around the line because of the sheer size of the non-probability sample. So just as we did with the continuous Y, we can look at specific numeric summaries to get credible intervals for the MUBP. Using the median as our point estimate, we get about a bias of about almost 20 percentage points, with a lower bound of 8 percentage points and an upper bound of 44 percentage points. So it's a relatively wide credible interval. I will note that the median there is, of course, essentially equivalent to phi equals 0.5, right? It's a uniform 0, 1 prior. The midpoint is going to be 0.5. So if we needed a single estimate of the bias, the phi equals 0.5 is what we generally say, use that. If you have no a priori knowledge and you want there to be one number, use 0.5. And in this case, the true bias, because we know that true proportion is 0.614, is 0.21. And the median MUBP is, if we round, 0.20. I mean, it's almost spot on. And I love to tell people that when I did this analysis the first time and I saw this, I nearly wept because I was so excited about how precise it was. Like, oh my gosh, this method really works when we have this in this particular instance, where sort of all the stars have aligned in that non-ignorable selection is really truly very believable and possibly very strongly at play in this particular example with this particular data set in this particular point of time in the United States. So that's being Bayesian. We can also use the maximum likelihood estimate or the modified maximum likelihood estimates. And here is where there was a question earlier about in the continuous code, we just used the mean of the proxy from the Bayes function and to feed into the maximum likelihood function. If you have to hand calculate it, that's what I'm doing here. So I am pulling out the coefficients from the probit fit with that as vector coefficients of fit. So that's my beta hats from the fit from the selected sample. And then I am just multiplying that by, I'm doing some vector multiplication to basically be plugging in the means for the z bars. So that line of code that assigns to the object x0 mean takes beta hat 0 plus beta hat 1 times the mean of in the population of the first predictor, beta hat 2 times the mean of the second predictor, etc. And now I get x0 mean, which is just a scalar. So that's the mean of the proxy in the non-selected sample. And then I calculate the variance similarly, again, using the matrix manipulation. So that would be the code you would use if you weren't using the Bayesian function to get out the mean of x. Now we have what we need in order to get the modified MLEs. This function requires you to run it separately for every value of phi. So if you want to calculate it at phi equals 0, and then again at phi equals 0.5 and phi equals 0.1, you don't send in a vector of phis, you just send in, you have to run the function multiple times. So here I'm showing phi equals 0, phi equals 0.5, and phi equals 1, where the inputs are the microdata, right, that proxy vector for the selected sample, the y vector for the selected sample, and then the mean and variance for the non-selected sample. It also requires the selection fraction and the phi value. The verbose equals true controls whether or not it is printing things out. So we can see that these estimates are very similar to what we get from the Bayesian approach, where that MUBP of 0.5 is about 0.196, very close to the median from the Bayesian with the uniform prior on phi. This code also repeats for you what the biserial correlation is. And of course, no matter what your phi value is, you get the same biserial correlation. So we have this evidence of that there may potentially be some pretty substantial bias in the proportion. So we can go back and take our unweighted mean, that's the mean of y1 in the code here, and just adjust it based on, in this case, I'm using the draws of the MUBP from the Bayesian approach. So in the continuous case, we had to do this multiplied by the standard deviation because the bias measure was about how many standard deviations away it was. For proportions, it's just a simple difference, so there's no scaling going on here. It's a simple subtraction. And if we run this, we see that our estimate of the adjusted mean is 0.63 with a credible interval from 0.38 to 0.74. And again, the truth is 61.4%, so that this estimate happens to be incredibly close. Phi equals 0.5 is really, really close to the true answer in the US population. One thing that's important to note is that even though we have a really large sample size, there's a pretty big credible interval here. So there's a pretty big difference between assuming complete ignorability, and complete non-ignorability. So these are some pretty wide intervals, but it is moving that estimate in the correct direction. And in this case, 0.5 happens to be just about the right answer. One of the things that is nice that people like to do a lot of times with binary variables is you can very easily get the worst case scenario estimates by assuming everybody who's not in your sample is a 0 or everybody who's not in your sample is a 1. These are often referred to as the Mansky bounds. We can't actually do that in this case, right? Because the US population is 250 million people. If we assume they were all unvaccinated, our proportion vaccinated would be 0. If we assume they were all vaccinated, it'd be 100%, right? So these are, even though these bounds are wide, they're much more useful than other kinds of sort of bounds that are used to bound estimates about proportions.
Just want to reemphasize too that we had a stronger proxy in this case, right? It was about 0.64 was the correlation. Even with that, you see a relatively wide interval. But the stronger, an even stronger proxy yet would further shrink that interval. So remember that the uncertainty, the amount of bias, and therefore the adjusted estimate is going to be a function of how strong of a proxy we're working with. So we were better in this case, but ideally we'd want something even higher than 0.464 or whatever it was. So we're going to come back to that in the next example.
Any questions about this example or the MUBP in general?
Chat questions or anything? Okay. Okay, great. Thanks, Rebecca. I'm going to turn back to the slides and we're going to jump into, again, there's a summary slide on 49, just kind of wrapping everything up from that particular example. But again, very good performance of the adjustment. And again, like a standard weighting approach would just completely miss the boat. And that's kind of the message here. So, okay.